We will look at another circuit called decoders. A special case of decoder we have already seen, which was for a 7-segment display. So this is a simple decoder where we have a binary code and we want to decode it to which of the digit it represent, or which number it represent. So let's take a 3-bit input. So if there are 3 inputs, then the 3 inputs can be so if there are 3 input, then I can have a maximum of 8 outputs. Okay, so in order to distinguish between the number that 3 bits are going to represent, so it's a code that I have. So binary code, code is getting decoded. Okay, so let's look at the setting of the problem. So I have first I will represent it like a black box. This is my decoder, so 3-bit decoder. So there are 3-bit input. Let's call them A, B, C. So it can be in one of the 8 possible ways, this combination of A, B and C. Then at the output I can have 8 outputs, 1, 2, 3, 4, 5, 6, 7, 8. I can call them as D0, D1, D2, D3, D4, D5, D6 and D7. Now what is D0? D0 is equal to 1 only under one condition. It is equal to 1 if the code is, that is ABC, is equal to 0, 0, 0. Okay, then only so it's not the way to write. So D0 is equal to 1 if ABC is equal to 0, 0, 0, and it is equal to 0 if ABC is otherwise. Let me write otherwise. So similarly each of this bit. So here it is D7. So this is equal to 1 if ABC equal to 1, 1, 1, 0 otherwise. So this is the functional description of the decoder. So input can be only in one of the 8 different combination or possibilities, and the output will be, one of the output will be set to high depending upon the input combination. So that is what the functional description of decoder. One more thing I can show, say D3. So D3 is going to be equal to 1 if ABC is equal to 0, 1, and it is equal to 0 otherwise. Okay. Now if you write the truth table of this, so A, let me see, truth table. We can specify the functionality of any combinational circuit by writing its truth table. So A, B and C, and the outputs are D0, D1, D2, D3, D4, D5, D6, D7. So you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are the possibilities of the input combination. Now, as said in the above functional description, I said D0 equal to 1 only if ABC equal to 0, 0, 0. So this is 1, and then this is 0, 0, 0, 0, 0. All other case it is going to be 0. Only if the input is 0, 0, 0, then only D0 is going to be 1. Whereas D1 is going to be 1 only when the combination corresponds to the binary code for 1. In all other case it is 0. It has to be 0. So any detection of binary code corresponding to 1 comes at the input, D1 will detect that. Similarly, D2 will detect 2 and nothing else. And D3 will detect the code for 3, binary code for 3, and D4 will detect the binary code for 4 and nothing else. And D5. Okay, so this is the truth table for decoder. Now the question is, how can we implement this? What is the circuit which will implement this? Okay, so the circuit is not very difficult. It is very, since there is only one, if you draw the K map, there are 8 Boolean function D0, which is a function of ABC, and there is only one case in which it is equal to 1, then basically it is that min term only. Right? There is no grouping possible, so you can just directly write the expressions very easily. You can say D0 is equal to A bar, B bar, C bar. D1 is equal to A bar, B bar, C. D2 is equal to A bar, B, C bar. D3 is equal to A bar, B, C. D4 is equal to A, B bar, C bar. D5 is equal to A, B bar, C. This is 1, 0, 1. D6 is equal to A, B, C bar. And D7 is equal to. So these are basically the min terms. This is ABC. So this is basically M0, M1, M2, etc. And this is M7. So these are basically min terms. And generating them is very easy and direct. So oftentimes what happens is that there will be an enable pin in addition to this, and the enable pin can be either active low or active high input, Suppose if it is active low input, there will be a bubble like this. That means this entire chip, okay, if you consider it as a chip with 3 input and enable pin input and then 8 output, so this chip will be activated only when E is equal to so E is equal to 0 enables the chip and 1 disables the chip. That means even if you give an input, there will be no output. I mean, the output will be not function. Okay, it will remain as either a high impedance state, or it could remain as 0. All will be remaining as 0. But if it is working, one of the outputs should always be high. Okay, and decoders are of 2 types also, which I did not mention. Either it could be active high output or active low output. Okay, so active high output means whenever a particular combination of input code is detected, the corresponding line will be set to high and all other outputs will be remaining at low. So that is active high. So the chosen line corresponding to a particular code will be made to high. Whereas active low means when you write the truth table of active low, it is active low. Wherever it is 1, it is 0, and wherever it is 0 at the output, it is 1. So that means the line, whenever it is detecting a particular code, that line will be made to 0. So that is active. So these are 2 variations of the chip. And similarly, the input which is enable input, that also can be either active low or active high.
Sir,
Yeah.
sir, what is the significance of using enable pin, sir?
Enable pin is basically to deactivate a particular chip. Every chip will have an enable pin. If you disable, for example, if you give a 1 here to this chip, it will be disabled. That means it will not respond to the input, and all output will be in a high impedance state. That means as if neither 0 nor 1, nothing is connected to the output. Is that clear?
Yes, sir. Sir, then what is the use of this decoder?
No, yeah, basically this becomes useful in a larger circuit where this is a part of the circuit. If this decoder becomes part of a bigger circuit, then certain times disabling can be beneficial. I can discuss one example. So implementation of this circuit is quite easy. Basically you need all so you have so just let me just complete this implementation, and then I will come back to your question. So you have A, in direct form as well as in complement form. Direct form I put like this, and complement form I put like this. And similarly you have B, direct form and complement form. So this is B, and then you have C and complement form. Okay, so to generate M0, that is our D0 output, we just need to, and let's say there is a enable input also, which is let's say here enable. So enable input, since we are putting E bar, so we are taking E bar. So we will take a complement of that, and then I will not show all the output. So this is our D0. So D0 is A bar, B bar, C bar, and this will be only when E bar is 0. So there will also be E bar here. Enable pin is 0. So if this input is 0, then the complement of that, okay, if E bar is 0, only when only then we will have this D0 becoming 1 if it is active high. If it is active low, I have to put a NAND gate instead of AND gate. So that is the difference. So similarly, two more I will just show. The next case is so this is D1. This is equal to A bar, B bar, C into E bar. So this way I can go on for all the terms, and the final term if I show, so that will be A, B, C, and then so this is D7, which is A, B, C, E bar. So is this implementation clear? This is how this circuit has a lot of application. It can be used to generate any logic function also, because ultimately all the logic functions are going to depend upon the minterms. So if you have all the minterms present, then whichever minterm which are present in a particular function, you can just pick them up and implement any boolean function. And one of the area where it is having huge application is memory design, like ROM design. ROM is basically having decoder and then a set of OR gates. We will discuss those things also later. Is this implementation clear to you?
Yes, sir.
Okay. So now coming back to your question, what is the use of enable? Okay. So one good example which I can give you is that problem. Okay. Design a 4 by 16 active high decoder using two 3 by 8 decoders. Design a 4 by 16 active decoder using two 3 by 8 decoder. So if you want to do this, then it is necessary that you have a enable pin. So let me draw those two 3x8 decoder. So this is number 1, 3x8 decoder. So 3 input, A, B, C, and it has output, which I am going to call as D0, D1, D2 up to D7. And then I have another uh, 3x8 decoder. Here also I give A, B, C. So D0. Okay, so this I will now going to name it as D8. I'm going to call with the different names, D8, D9, etc. So 8 to 15. So 8 number of outputs here, and only difference is that I give the same input but the outputs are named differently, otherwise everything is same. And then this as an enable pin. This is our enable pin, which is an active low. So enable bar. So the fourth input, that is D input, what I will do is that I will give it directly to this. So what does that mean? So D is given directly to this. When D is equal to 0, the above will be activated, and that is going to make one of the output line of the first decoder high, depending upon the ABC combination. And then what I do is I take a NOT gate and if D is equal to 1, this NOT gate will make this second one activated. If D is 1, then the second one will be activated, and one of the outputs of the second decoder will be made to work. Okay, so the other the first decoder will all be 0, output will be 0, so which I can actually incorporate in the truth table. The enabling bit information I have not put it in the truth table. So this is E equal to 1. Sorry, E equal to 0. Enable equal to E. Enable bar. Enable bar. If it is 0, this is what is happening. Okay, enable bar is an input. If it is equal to 0. Now if enable bar is 1, it doesn't matter what is here, everything will be 0. All outputs will be 0. Okay, so let us consider like this. So if enable bar is high to a particular 3-bit decoder, then all the output is equal to 0. But if enable is 0, that means the chip is enabled, one of the output is going to become 1. That depends on the code at the input. It will depend on the input. But if enable is high, then it doesn't depend on the input and everything is going to be set to 0. So this is the way enable pin will work. Now if you look at here, I have given the D to the enable input. So if D equal to 0, the upper decoder will do its function, whereas the lower decoder will all have a 0 at the output. Okay, so that happens if the numbers A, B, C, D is representing a code which is less than 8. If it is less than 8, D is equal to 0. So if D is equal to 0, then A, B, C, D represents a number, a binary number less than 8, less than 8, and therefore we can show a number which is less than 8 with D0 to D7. Therefore D0, D1 up to D7 will show the decoder output. Whereas if D is equal to 1, what will happen? A, B, C, D represent a binary number. This is D number greater than 7. Therefore D8, D9 up to D15 will show the decoded output. So is that clear?
Sir,
Yeah.
for D equals to 1, E n bar still will be 0, sir.
Repeat the question.
Sir, for D equals to 1.
If D equal to 1, what is going
Yes,
to
sir.
happen is that this lower 3-bit decoder will be activated. The upper one all will have D0 to D7 will be 0, and for the lower one, depending upon ABC, it will show one of the output as high.
Yes, sir.
Yeah. Because if you can take an example of say A, B, C, D example is equal to say 1, 1, 0, 1, 0. Let's say A, B, C, D is equal to 1, 0, 1, 0. So this corresponds to 10. Okay, so this binary code corresponds to 10 in decimal. So that means I want D10 to be activated, and since our D, this is our D is 1, the upper one all will be 0. That's what I want. Okay, all will be 0, so this will be 0, this will be 0, this will be 0. Similarly, all of this will be 0, and the lower one will be activated, and now the output is going to depend upon ABC. ABC is 0, 1, 0, which is 2. So this will be 0, this will be 0, this will be 1, and all other things will be 0. Okay, this is 0, 1, 2, right?
Yes, sir.
Yeah. So I said M0, M1, M2 up to M7, and this is also M0, M1, M2 up to M7. So corresponding to 2, because this number is 2, 0, 1, 0. So D10, which I labeled as D10, which is M2, for the lower decoder, that will be 1, and all other will be 0. And that's basically a 4 by 16 decoder operation. So this is an example how to use a enable pin to make the 3-bit decoder as a part of a bigger circuit. So in this case, it is a bigger circuit is a 4 by 16 decoder. Okay.
Yes,
Now the opposite of a decoder is encoder. Encode. So let's consider 8 by 3 encoder. Now this will have a decoder input. You have to make a code corresponding to it. So you will have D0, D1 up to D7, and then you will have 3 output, which is say ABC. So this is 8 by 3 encoder. 8 by 3 encoder. Again, the truth table will look exactly the same. Only difference is that what was earlier output becomes input here, and there are 8 inputs. So D0, D1, so truth table. D2, D4, D5, D6, D7, and then you have the output A, B, and C. Okay. Okay. So the first case is this one is 1 and everything else is 0. If it is active high input, it could be active low input also, in which case you will have the complement of this. Okay, 0, 1, 1, 1, 1, 1, 1, etc. That is active low. But what I am drawing is active high. Active high inputs. So this will correspond to a code 0, 0, 0, and then 0, 1, 0, 0, 0, 0, 0, 0. This will be 0, 0, 1. Next 0, 0, 1, 0, 0, 0, 0, 0. If this is the case, it corresponds to code 0, 1, 0, 1, 0. And then 0, 0, 0, 1, 0, 0, 0, 0. And that will be 0, 1, 1. And then 0, 0, 0, 0, 1, 0, 0, 0. And that will be 1, 0, 0. 0, 0, 0, 0, 0, 1, 0, 0. And that will be 1, 0, 1, which is 5. And next is 0, 0, 0, 0, 0, 1, 0, 1, 1, 0. And finally we have the first 7-bit 0 and the last bit 1, which is 1, 1, 1. Now if you try to solve this Boolean function to find the circuit using K-map, you will be end up in trouble, because there are 8 inputs. A is a function of A, which is an output. Now it's a function of D0, D1, etc. up to D7. So if you try to solve this using K-map, you will end up in trouble. Why? Because there are 8 inputs. We can solve up to say 6 variable K-map, we can manage, but beyond 6, K-map is not a good way to solve Boolean functions or simplify Boolean functions. But unfortunately, things are not very difficult here. Fortunately, things are not very difficult here. If you look at the A column, it becomes 1 when either D4 is 1, D5 is 1, D6 is 1, and D7 is 1. So you can write it as D4 plus D5 plus D6 plus D7. So a 4 input OR gate can perform this. So similarly, if you look at the next output, which is the B output, D2 and then D3, then this one. So these are the three, D3, D. So you can see D3 and D. So D2 and D3, and similarly you have the last two, D6 and D7. D6 and D7. So that will give you B. Now C, in a similar manner, if you look at alternatively, C is 1. The first bit it is 0, so D1, all the odd ones, D3, D5, D3, then D5, and then D7. Okay, so this way we can manage, and it's quite easy to implement this. So if you have all the D's available, you just use a 4 input OR gate to work it out. So D0, D1, D2, D3, D4, D5, D6, D7. So these are the inputs. And then if you just take a OR gate of this, okay, so that is your A, and B is, I think, D2, D3, D2, D3, and D6, D7. Those are the cases where the second bit is 1 and the first bit is 1, or the LSB bit is 1, then odd number D1, D3, D5 and D7. Okay, so these are the cases where, so you can find, so this is the circuit. It doesn't depend upon D0 because we are considering cases where the output becomes 1. Okay. So the output can be 1 only under these conditions, so which are given by the 4 different cases by looking at the truth table. Any doubts in this? Any doubt in this circuit? This is encoder circuit. by 3 encode. Now there is a variation of the encoder circuit which is called priority encoder. Priority encoder. Now what the priority encoder do is like it is allowed to have multiple input becoming one. So let's say if I say about 8 by 3 priority encoder. So then there is D0, D1 up to D7. So multiple inputs at the same time are allowed to be 1. Earlier case that is not possible. Okay, it is restricted only to one particular input becoming 1. So here only one of the input is allowed to be 1 at the input. Okay, so D0 to D7 only one of them is allowed to become 1 at a time. So either D0 is 1, if D0 is 1 all the other has to be 0. If D1 is 1 then D0 and D2, D3, D4, D5, D6, D7 all of them should be 0. So that it is very restrictive. Whereas in priority encoder often we find that type of application. There are multiple inputs but there is no restriction which one is 1. Now if multiple things are going to become 1, then how do we write the output, which is again 3-bit. So A, B, C. So we have to assign some priority, either ascending order, descending order, or whatever priority that you want. Then the highest priority case, which becomes 1, the code corresponding to that will be assigned to ABC. So as an example, let us show the truth table. Any questions? D0, D1, D2, D3, D4, D5, D6, D7. Okay, so we have to assign a priority. Either D0 is the highest priority, or D1 is highest priority, or you can say ascending order, descending order. So let's take a case where the priority for D7 is higher than. So this has higher priority than this. This has higher priority than this. Okay, so this way. This is the order of priority. And so if this is 1 and all the rest is 0, then your ABC, so this is one way it can happen, or it can happen this one, all the rest is 0. I can say this is X. Doesn't matter whether and then X1 0 0 0 0 X 1 0 0 0 0 X 1 0 0 0. Again x x x x x 1 0 0 x x x x x x 1 0. Finally the last one is 1, then x x x x x x. So when the highest priority input is 1, we don't care about so that's why the don't care comes here. We don't care about the lowest priority. The code will be entirely decided by the highest priority. Here I have chosen this ascending order of priority, but it could be any way that you require. Accordingly the truth table will differ. Now, so this case you will have 0 0 0, and this one will be 0 0 1, this one will be 0 1 0 0 1 1, then 1 0 0 1 0 1 1 1 0 1 1 1. So these are the
Sir,
yes.
can we have D6 and D7 1 at the same time?
Yes, yes. D6 and D7 can be 1. That is taken care of by the last row. It is don't care means I can have it 1. I can have all of it equal to 1.
So the above one. Say about the D7 prior D6 when D6 is 1, then we got D7 as 0. So
Yes.
if we make D7 as 1,
That then that will be the last case. If D7 is 1, you can have multiple possibilities for all other bits. So that is taken care of by the last row.
okay, yes sir.
Yeah. But if D7 is 0 and D6 is 1, then that is taken care of by the previous row. So we are taking care of all the cases. That is, how many cases are there? There are 2 raised to 8 cases, right? 8 inputs are there, so 256 cases are there, and all 256 we are taking into account. So you see that 256 cases means we need a K-map with 256 cells to solve this problem. So so it is we have to try to solve it in a different way. So let's look at the A output. We look at the A output. So A output, which is a function of D0, D1 up to D7. So these are the cases where it becomes 1. So if D7 is 1, we can be sure that output is 1. Now if D7 is 0, then I have to look at D6. If D6 is 1, then also I can make it 1. The other way is D7 bar, D6 bar, and D5. So that also become 1. The last case where A can be 1 is I have D7 bar, D6 bar, D5 bar, and D4. So these are the 4 different ways I can make A equal to 1. There are 4 cases which are denoted here. Okay, these 4 cases. So each of them correspond to one term here. So without going into a K-map, we have to write the expression. The next one, B, D0, D1 up to D7. Now yeah, so look at the cases where B is 1. So there are 2 cases here and 2 cases here. So let's write it as B is equal to 1 when if it is D7, definitely we have to make it 1, and then or if D7 is 0 and D6 is 1, then also we have to do that. Then the case is here, this one, so that is D7 bar, D6 bar, D5 bar, D4 bar, and then D2 plus again. So what I can do is I can take this inside and write D3 bar, D3 bar, D2. So this way I can write it. Now there is some simplification possible. So this is, since I am not using K-map, this doesn't mean that whatever expression I got is a very simplified expression. If you look at what is in the bracket, I can simplify this. I think the simplification is possible in the previous case also. For example, this one I can simplify it as, D3 plus D3 bar into D3 plus D2. And this is 1, and therefore it is D3 plus D2. So this way I can replace this bracket in this manner. So this is equal to, and same thing goes with the first 2 term also. So if I do this, I can write it as D7 plus D7 bar into D7 plus D6. So this is again 1. So this becomes D7 plus D6 plus D7 bar, D6 bar, D5 bar, D4 bar into D3 plus D2. Okay, so which is quite simplified compared to the first way we write. So same thing applies here also. You can simplify between these two. And and again we can take out this and simplify here also. So whatever expression I wrote, it is not necessarily the simplest expression. So let me write here. So this can be written as D7 plus D6, and then if I take D7, D6 outside, I can write it as D5 plus D4. D7 bar, D6 bar, D5 plus D4. So this is the simplest expression. Okay, so now finally C D0, D1 to D7. So this is equal to, so alternatively, so D7, then we have D7 bar, D6 bar, D5, then D7 bar, D6 bar, D5 bar, D4 bar, D3 plus D7 bar, D6 bar, D5 bar, D4 bar, D3 bar, D2 bar, D1. Okay, yeah, so that is the expression for C. Okay, so this is priority encoder. The priority encoder is allowed to have any number of bit equal to 1, but the code that is produced at the output corresponds to the input which is of the highest priority, which is made to 1. Often the priority encoder or encoder also comes with an additional output which is called valid output. So we, just to signify the code is valid, and if there is an additional output, you can make use of enable input pin also, enable bar, because when you give enable equal to 1, enable bar equal to 1, then the entire shift will be disabled and the all output will become 0, 0, 0. Okay, but if it is D0 alone is 1 and all the rest of the input is 0, then also you have ABC equal to 0, 0, 0. So to distinguish between these two cases, we have an additional output. So if you are putting enable input, you need to introduce a valid output. Okay, so incorporating this, if I write, so let me write enable bar. So here it will be 0, 0, 0, 0, 0, 0, 0. So then the valid output is in this case is going to be 1. So there will be an additional output which is B. So this will be 1, 1, 1, 1, 1, 1, 1, 1. Now the moment enable input becomes 1, then it does not matter what is the input, does not matter what is the input from D0 to D7, the output is invalid. The output is 0. Okay, so V is 0 means we don't look at We don't take ABC as CDC. Could be anything there. Sorry, it is not anything, it is 0. It is not anything, it is 0. So this will be 0, but you should not confuse this with this case. These two cases should not be confused. So introducing enable can make all the output to go to 0, but in order to say that it is different from the case corresponding to the first row, so that is why we have introduced a valid output. So the encoder require a valid output in order to specify or distinguish between the effect of enable pin and the case where only the D0 is equal to 1. Alright, I will stop here.